Hello class, we're about to start lesson 2-2, 88 miles per hour. We're also going to cover a small portion of 2-3 as well and finish up 2-3 tomorrow. But your check assignment you will need to do tonight for section 2-2, and then you will do section 2-3 check assignment tomorrow. Okay, for lesson 2-2, we have 88 miles per hour. Our lesson objectives is to compute rates of change and compare it to ratios and conversions factors. Interpret and use rate of change, and then convert units involving rates. Okay, just need to move this over, adjust this just slightly. Okay, now we go down here to the bottom of the page. It says a rate is a ratio that compares two quantities. By rate of change, we mean a rate that compares the change in one quantity to the change in another. A speed like 88 miles per hour qualifies because we can write it this way: 88 miles divided by 1 hour. This quite literally compares a change in distance, 88 miles, to a change in time, 1 hour. We call it a unit rate because its denominator is 1. Now it says list some unit rates you're familiar with. So you could say 50 feet per second, per 1 second, $9 an hour, or you could say $3.50 for 1 box. Those are examples of unit rates that most of us are familiar with. Or let me add in one more thing here. $2.49 per gallon. And we know with gasoline. All right, so now we go over to the next page. Now for number 2, it says list some rates that aren't unit rates. Now remember, unit rates specifically state that it must be divided by 1. So with that in mind, if we took $100 for 8 hours, that is not a unit rate because it's not divided by 1. We have 240 miles for 4 hours, and then $1 for 0.25 miles. Now it says compare rates of change and conversion factors, which we studied in lesson 1-5. How are they similar? How are they different? Okay, now they are similar because both are fractions. Comparing two quantities. And then, for example, if we took 88 miles for 1 hour, and then we take 12 inches for 1 foot, and then we could say both are conversion factors, but not necessarily rates of change, or I should say unit rates. Well, I could say rates of change. Okay, now it says here, in fact, let me move this up just slightly. All right. It says, let's explore the idea of rates of change as a comparison between changes in two quantities a little more. According to the U.S. Census Bureau, about 2.7% of registered nurses in 1970 were men, compared to 9.6% in 2011. In 2011, the average salary for the male nurses was $60,700 per year, while the average annual salary for female nurses was $51,100. How much did the percentage of male nurses increase from 1970 to 2011? So we want to notice the increase. So we'll take the current value minus the previous value. And we know these are both percents. So it'll be 6.9%. That's how much it has increased. Now, how many years passed in that time span? We had 2011 minus 1970. That'll be 41 years. Number 6, divide your answer from question 4 by your answer from question 5. Include units in your answer, which come from the units in the division. What does your answer tell you? Why is it a rate of change? Okay, so basically we had 6.9% over 41 years. Now, if we put that in our calculator, let me pull up Desmos here. So if we take 6.9, we'll just leave it at 6.9. We're not going to alter it for it being a percent yet. So we'll do 6.9 divided by 41. So if we round that to 3 decimal places, this will give us 0.168, and it still will be a percent all over 1 year, because that decimal is divided by 1. So that would give us 0.168% over 1 year. And then we could rewrite this. A lot of times you will see it written like this as 0.168% per year. Or you could see it as 0.168% divided by year. And these all mean the same thing. Okay, now, let me move this out the way. Okay, now it says, why is it a rate of change? And then it also asks us to tell us what the answer tells us. So you could say the percentage of male nurses increased 0.168% per year, and it is a rate of change because it compares a change in percent to a change in time. There wasn't that much room here, so I had to make some room. Okay, number 7. It says, find the rate of pay for women compared to men in 2011. Write your rate so that it has $1 in the denominator. So, women made $51,100. That was stated up here. Female nurse was $51,100 divided by the male nurse, which is $60,700. Now, the reason why we wrote it like this is because it says women compared to men. So women will go first and men will go second. Now, we will put this in our calculator. Got to go back and get the Desmos calculator. And we would take 51,100 divided by the 60,700. So if we round that to 2 decimal places, especially since we're dealing with money, it'll come out to be about 84 cents for $1. So basically, women nurses is 84 cents for women nurses versus $1 for male nurses. So basically, women make for every 84 cents that women make, the male nurse makes $1. So that's about a 16% difference. Okay, now we move on to the next page. It says, what does your answer to question 7 tell you about the gender gap in pay for nurses? What do you think is responsible for the discrepancy in earnings? Okay, female nurses make an average of 84 cents for every dollar male nurses make. Okay, now they also ask us, what do you think is responsible for the discrepancy in earnings? It could be sexism, differences in overtime, etc. All right, now it says explain why your answer from question 7 is not a rate of change. And the reason being is it compares two salaries, not two changes in salary. Okay, now we scroll down here. It says the word equivalent is an important word in math and one that we'll use often in this course. Make sure you clearly understand what that word means. Look it up and discuss it with your group if necessary. Number 1, if you make $100 a day for doing a certain job, how much money would you make in a 5-day work week? So if you made $100 for one day and you did that for 5 days, that would be $500. Now it says number 2, are $100 a day and $500 over 5 days equivalent rates? What does that mean? It'll be yes, both reduce to the same rate per day. Okay, now go here to the back. It says question 2 demonstrates a useful fact about rates of change. They can be scaled up or scaled down to fit a given situation. Scaling up a fraction is done by writing an equivalent fraction, that is one that has the same value, using larger numbers. Scaling down is writing an equivalent fraction with smaller numbers. These processes are done by either multiplying both the numerator and denominator by the same number or dividing both the numerator and denominator by the same number. Number 3, write a fraction equivalent to 60 miles over 4 hours that has 2 in the denominator. So we have 60 miles over 4 hours, but we want 2 in the denominator. So we ask ourselves, 4 divided by what is 2? And we know that's 2. So we'll divide the numerator and denominator by 2. So that'll give us 30 miles for 2 hours. Now it says for 4, write a fraction equivalent to 60 miles over 4 hours that has 1 in the denominator. So we have 60 miles over 4 hours. Now you could do one or two things. You could put this in your calculator. So let me show you that. You could take that 60 divided by 4. And that will give you 15. And you know that'll be 15 miles over 1 hour. Or you could have done this by hand. You could have taken the 60 miles over 4 hours and determined what you needed to divide the denominator by to get 1. And you would need to divide the numerator and denominator by 4. And that will give you 15 miles over 1 hour. Now, this next problem. It says write a fraction equivalent to $320 over 4 days that has 10 in the denominator. Hint, first scale down, then up. All right. So you have $320 over 4 days. Now we could take our calculator. So we could take 320 and divide it by 4. And that would give us 80. So this would be $80 over 1 day. Now remember, they want us to have a denominator of 10. So we ask ourselves, 1 times what is 10? We know that's 10. So we'll multiply our numerator and denominator by 10. So that will give us $800 over 10 days. And that will be our final answer. Now, we go here to number 6. If one bicyclist is pedaling at a rate of 40 miles in 3 hours and another at a rate of 50 miles in 4 hours, which is faster? So what we could do is we could take our 40 miles divided by 3 hours, and then we could take our 50 miles and divide it by 4 hours. So we could put that in our calculator. I may do the 50 first since I already have that over 4. So that'll be 12.5 miles for 1 hour. And then we would take 40 divided by 3. And that would give us, if we round it to 1 decimal place, that'll give us 13.3 over 1 hour. So basically, this is faster because 13.3 is larger than 12.5. So the 40 miles for 3 hours is faster. Okay, now we move on to the next page. It says most experienced runners get to a point where they can comfortably jog long distances at a consistent pace. This pace, of course, is another way to say rate of change, because speed is the rate at which distance changes compared to time. One particular runner jogs 1 lap around a 400-meter track in 2 minutes. In questions 7 through 15, you can assume that the runner can maintain this pace for a long time. So for number 7, it says for every blank minutes, the runner jogs blank meters. So for every 2 minutes, the runner jogs 400 meters. It says complete the table, continuing the pattern for times and finding the associated distances for this runner. So if you notice, we're going up 2 minutes. So this would be 6, 8, 10, and 12. And then here we'll be going up by 400. So it'll be 800, 1200, 1600, 2000, and 2400. Okay, number 9. It says, notice that the rate at which the runner's distance changes is constant. When the rate of change is constant, a quantity illustrates what type of growth that we encounter in linear in lesson 2.1. It would be linear because we're adding the same amount. Number 10, write the runner's rate as a fraction using meters in the numerator. All right, so we will have 400 meters all over 2 minutes. Now, we will not simplify this. This is one of the rare cases where we wouldn't simplify. Because if we go down to problem number 11, this is where we're going to simplify. It says, write this rate as a unit rate in meters per minute. So we would take our 400 meters divided by 2 minutes, and we would simplify that by dividing both by 2. So it'd be 200 meters over 1 minute. Now number 12, it says convert your rate from question 11 to meters per second using dimensional analysis. Round to 2 decimal places. So we have 200 meters for 1 minute. Now we want to change this to meters per second instead of meters per minute. So we would have to do a conversion factor. We know for 1 minute there are 60 seconds. And remember, they have to be diagonal from each other. So the units would simplify out the minute with minute. So this will give us 200 meters all over 60 seconds. Now we can put that in our calculator. So we add 200 divided by 60. And then we can round that to 2 decimal places. So it'd be approximately 3.33 meters over 1 second. Or you could write it as 3.33 meters per second. Either one is fine. Okay, now we move on to the next page. Now for 13, it says, what distance will the runner cover in 40 minutes? So if you look here, we will go back to the minutes. We have 40 minutes. And remember, it's 200 meters for 1 minute. We'll put this over 1. The minutes will simplify each other out. So it'll be 8,000 meters. Because you know this will be divided by 1. So it'll end up being 8,000 meters. Okay, now 14. What distance will he cover in 40 seconds? So we could take the seconds that we came up with. Remember, we came up with 3.33 meters in 1 second. We'll put this over 1 and the seconds will simplify out. And this will give us 133.2 meters. Now for 15, it says, what would the runner's total time be for a 10K race? Now it says 10 kilometers, that is. Recall that 1 kilometer is equal to 1,000 meters. Your answer to question 11 will help. Okay, so we had 10 kilometers. And then we know we have 1,000 meters is equivalent to 1 kilometer. Now they said that our answer from question 11 will help. So we go to question 11, that's 200 meters over 1 minute. Now that will help, but let's see what they're asking for. They want the total time for this race. So what we would have to do, since meters would be in the numerator, kilometers simplify out, we would have to put meters in the denominator here and the time in the numerator, because we want to know the total time for the race. So kilometers will simplify out, meters will simplify out. Now we're just left with time. So this would be 10,000 all over 200, and this would be minutes. So if you simplify this out, this end up being 50 minutes. Now that's of course if they maintain the same speed. Okay, now we come here to the bottom. It says here, as question 15 shows, when dealing with rates, sometimes it's necessary to convert the units in both the numerator and denominator of a fraction. For example, it's common to convert speeds from feet per second to miles per hour. Both feet and seconds need to be converted. Fortunately, dimensional analysis is a perfect tool for this purpose. Because the conversion factors we use equal 1, regardless of which unit is in the numerator. Just like 12 inches in 1 foot is the same as 1 foot over 12 inches. Okay, 16. The Earth moves at about 98,000 feet per second as it revolves around the sun. How fast is that in miles per hour? Now it says recall that 1 mile is equal to 5,280 feet. Okay, so this is seconds. They want us to, we go from feet per second. So it'd be 98,000 feet over 1 second. And we want to go to miles per hour. So now we could change our feet to miles. It's 5,280 feet for 1 mile. Now, the next thing we need to do, that'll take care of our miles. But now we want to go from seconds to hours. So first, let's go from seconds to minutes. It takes 60 seconds to equal 1 minute. And then we're going to go to minutes to hour. It takes 60 minutes to equal 1 hour. So the feet would simplify each other out. The seconds would simplify each other out. And the minutes would simplify each other out. So now, when we multiply all of this, this would give us, let me see, 352,800,000 divided by 5,280. Now we can show that in the calculator. So let me clear all this out. All right, so we could take 98,000, put a division here. Well, you know what, actually, no, let me just go with the 98,000 because I want to show what that numerator is. So 98,000 times 60 times 60. So that gave us 352,800,000. Now for our denominator, we want to divide that by 5,280. And that gives us, now they asked us to round, they did not ask us to round to a certain amount. So let's just round to 2 decimal places. So this will be approximately 66,818.18 miles over 1 hour, which is the same thing as 66,818.18 mph for miles per hour. So either one of those would be fine. All right, now we move on. Now our next page, we're not going to do that much from this page, and this is the last page of this lesson. We're actually going to do problem number 1. It says when advertising special financing deals, let me put this calculator down here. We're actually on page 130. It says when advertising special financing deals, Car makers often use rates to describe what your monthly payment will look like. This is because the amount you need to borrow varies widely based on the car you choose and the down payment you make. In January 2013, Hyundai offered 2.9% financing on the Genesis Coupe, which would result in monthly payments of $22.09 per $1,000 borrowed for 48 months. So, for every $1,000 borrowed, the monthly payment will be $22.09. Now, the last thing we're going to do here is complete this table. Now, for the table, it says complete the table of loan payments using the answer to question 1. So if you got 1,000, it's $22.09. 2,000, you doubled it, so it'll be $44.18. $3, you tripled it. So you could keep just adding $22.09. So it'd be $66.27, $88.36, and then it'll be $110.45, $132.54. Then we'll have $154.63, $176.72, $198.81, and $220.90. And if you notice here, for every 1,000 you go up, the payment goes up by $22.09. So that basically finishes up section 2.2. Now, I did tell you all that we would be doing part of 2.3. So I will let you know when we stop for 2.3, but we're on page 133 now. So this is lesson 2.3. And our lesson is titled Warning Graphic Content. Now, the reason why I'm starting 2.3 is because there's a bit of graphing here. And I think by us getting an earlier start today, we will be able to finish up 2.3 in totality tomorrow. Now, it says our learning objectives is to understand and use a rectangular coordinate system to connect data to graphs and interpret graphs, to define slope as a constant rate of change, to define and interpret the y-intercept of a line, and to write an equation of a line that models data from a description, table, or graph. Okay, now, it says if you've been paying attention to the news at all for the last several years, you know that the unemployment rate in the United States has been a big story. But what did unemployment look like before the economic crisis of the late 2000s? These tables display the average annual unemployment rate for the years from 1992 to 2011. Number 1, it says use the table to write a verbal description of trends in the unemployment rate over that 20-year period. So basically, if you notice here, it decreased from 1992 to 2000. It increased from 2000 to 2003. It decreased 2003 to 2007. It increased 2007 to 2010, then decreased in 2011. Well, actually, I should have said it decreased from 2010 to 2011. Okay, now it says with enough effort, you are probably able to write a reasonable description But because there's so much data in the table, spotting the trends isn't exactly a simple thing to do. Next, let's look at the same data displayed in a graphical form. Now, one thing I do need to show you is this here. I said that things decreased from 92 to 2000. If you notice, from 92 to 2000, it steadily went down, and then it started going up in 2001. So it went down from 92 to 2000. So you always start where it ends here. You would start with that same year, whether it increase or decrease. So it increased from 2000 all the way up to 2003. It decreased from 2003 to 2007. And then it increased from 2007 up to 2010, and then decreased from 2010 to 2011. Now, we move on to the next page. Now it says here, when I look at the graph, two things occur to me. It's a lot easier to see the trend than it was from looking at the table. And the graph looks a whole lot like a dinosaur. All right, number 2. It says use the graph to write a verbal description of trends and the unemployment rate. Then explain why the graph makes it easier than the table did. So basically you could look here from 1992 to 2000. So you could say decreased from 1992 to 2000. Then you could look here to increase from 2000 till about, it's a little past 2002. So we assume that that's 2003. So it increased from 2000 to 2003. And then when you look at that from 2003, it looks as though till about 2007, it was going down. So it decreased from 2003 to 2007. And then it increased from 2007 to look like 2010. And then it decreased from 2010 to 2011. So basically the same thing that we noticed from the table, but it was easier. It is easier to spot the data in the graph than a table. Now, without the numbers running along the bottom side of the graph and down the left side, we wouldn't be able to understand any of the information the graph provides. Those numbers provide the scale for the graph, and they're always crucial in drawing a graph. Each of the number lines that we write the scale on is called an axis, the plural of the word axes. In preliminary numbers released in early 2013, the average unemployment rate for 2012 was listed as 8.1%. We can add that piece of information to the graph by finding 2012 on the horizontal axis and 8.1 on the vertical axis. Then drawing imaginary lines up from 2012 and right from 8.1 until the lines meet. That's where we put the point corresponding to 2012 and 8.1. So they showed that here. This would be 8.1, and then also the line here. Okay, now it says, notice that when we found the location to indicate that the unemployment rate was 8.1% in 2012, the imaginary lines we drew formed a rectangle with the two axes. That's why we call the system of graphing a rectangular coordinate system. Each of the numbers we use to locate that point are called coordinates. The horizontal axis is usually called the x-axis, and the vertical axis is usually called the y-axis. The point where the two axes meet is called the origin. Since we didn't need to worry about negative years or negative unemployment rates, the graph we drew earlier only showed positive values along each axis. But there are plenty of examples of data where negative values make perfect sense. So a rectangle coordinate system is often set up like this. Now, the origin is where they meet at right here. Okay, now, the process of locating information on a rectangular coordinate system like the 8.1% unemployment rate in 2012 is called plotting points. We identify locations by writing the two coordinates together inside parentheses like this. We had 2012 and 8.1. What are the coordinates of the origin in a rectangular coordinate system above? The origin is always 0, 0. X is 0 and Y is 0. Now it says here, look carefully at the numbers on each axis. What distance does each box on the grid represent along the x-axis? What about the y-axis? These distances are known as the scale for each axis and are always carefully chosen so that all of the points fit nicely into the space provided. Choosing a reasonable scale is the first step in drawing any graph. The x-axis, if you look here, this is 0, and we go to 20, and it's 5 spaces. So it'd be 4, 8, 12, 6, 16, and then 20. So the x-axis counts by 4 units. And the y-axis, if you look here, we go from here to 50. We're going by tens, well, negative 50 and positive 50. So it'll be 10, 20, 30, 40, 50, negative 10, negative 20, negative 30, negative 40, negative 50. So the y-axis counts by 10 units. Now it says plot each of the following points on the rectangle coordinate system. Label the coordinate of each point. Now, here's the thing that I want to explain to you. Before we get into the labeling, I want to tell you this. You plot your point where the y-axis ends at. Again, wherever the y value ends at, that's where you plot your point. So, we look at the x values, the x coordinates. Now, the x coordinates go like this. It could go left, right, or stay. That's the only thing that the x value can do. It could go left, right, or stay, and we always start at the origin. The y value can only go up, down, or stay. Again, the y value can only go up, down, or stay. So let's go here to the origin. We start here. So x is 16. So that means we will go to the right because it's positive. So it'd be 4, 8, 12, 16. So that's the x value. Now we do the y value because remember, we only plot the point where the y value stops at. The y value is 0. So that means that it stays here. So we will plot that point. Now I'm going to write down the little letter A to let us know that that's the A. Okay, B, 0, 10. We go to the origin. Since x is 0, we stay here at the origin. Now we go here to the y. Y is negative 10. That means we go 1 down from the origin because these count are 10 units. So we will plot our point here. So this is our B. Now C, we had negative 8, negative 20. So we'll go back to our origin. We'll go to the left 2, which will give us negative 8. And then we would need to do our y value, which is negative 20. We'll go down 2. So that would be our C. Now finally D, go back to the origin. We will have to go to 12. So that means these are counted by 4. So we will go 1, 2, 3, because that's 4, 8, 12. Got to take care of our X. Now we have to do our Y. Our Y is a positive 35. Now remember, our Y's go by tens. So we'll go 10, 20, 30, and then we want to go 35. So it'll be in between 30 and 40. It'll be right here in the middle. So that would be our D. So now we have plotted all of those points. Now, we go here to the next page. It says, being able to understand the connection between a graph and the information that it illustrates is not just the most important skill in graphing, it's the reason that graphing was developed. If you can't interpret the meaning of a graph, it's just really bad art. A small plane takes off from a regional airport. Its altitude at various times is recorded in the table below. Write ordered pairs of the form flight time, comma, altitude. So flight time would be our X, the altitude would be our Y. For each pair of values, then plot the points on the graph. Okay, so flight time is 0, altitude is 0. And then here is 10 to 4,000, 20 to 3,000, 30 to 2,000, 40 to 2,000, 50 to 1,000, and 60 to 0. Now, the next thing here, we have altitude. Okay, listen. Where the X and Y meets, that is the origin. The origin here is 0, 0. So they tell us our first point here is 0, 0, which goes here. Now our second point is 10 to 4,000. So we go here to 10, we go up to 4,000. Next point, 20 to 3,000. So go here, 30 to 2,000, 40 to 2,000. And then we would go 50 to 1,000, and then 60, 0. So now it says, number 7, connect the points you plotted to draw a graph and describe what the graph illustrates. Then add a verbal label to each axis that describes the information it represents. So now, we'll go here. So that is our graph. Now we connected the points. The graph illustrates the altitude of the plane in feet based on the number of minutes since the flight began. Okay, now it asks us here, it says then add a verbal label to each axis that describes the information it represents. It actually already has that with the flight time and the altitude. We actually have that already. So we're actually done with that. Now, we need to move on to the next page. It says here, for questions 8 through 13, explain how you got your answer using both the table and the graph. The point is to make sure you focus on the connection between the information in the table and the height of points on the graph. What was the highest altitude reached by the plane? Now, if you look here, all you have to do basically is look at the Y value. The highest Y value, either looking at the table, you see the Y value is 4,000, or looking at the graph, this is the highest point. So it'll be that both agree, the table and the graph, 4,000 feet is the highest altitude. How long after the flight began did the plane reach its highest altitude? Now, if you look here, 4,000 reached after 10 minutes. Here is after 10 minutes. So it'll be 10 minutes. When was the plane flying level? Now, when it says flying level, that means that it remained the same altitude. And that was from 30 to 40 minutes. It remained at 2,000. So it'll be 30 to 40 minutes. And you could also see that on the graph too. 30 to 40 minutes is the same. How long did the flight last? If you look here, we started at 0 for the altitude, we ended at 0 for the altitude, and that was 60 minutes. And here, we started here at the lowest point to the lowest point here. So it's just 60 minutes. Number 12, when was the altitude of the plane increasing? Okay, if you look here, the altitude only increased from 0 to 10 minutes. So it'd be 0 to 10 minutes. After that, it went down or stayed the same and then went down some more. Okay, now we move on to the next page. It says, when was the altitude of the plane decreasing? Well, now, the plane actually decreased from 10 to 30 minutes. And we could look at that here. From 10 to 30 minutes, it went down. And then it started going down again from 40 to 60, because we cannot count the 30 through 40. Okay, could you please hold for 1 second? Okay, so let me write that down. It's supposed to be and 40 to 60 minutes. Now, number 14. It says, explain why we didn't bother to include negative values along either axis when drawing the rectangular coordinate system for the altitude graph. What would it mean if the graph ever has a height below the x-axis? It was non-negative amount of time So basically what this is saying is you cannot have a negative amount of time. And then the plane would have to go underground for the height. And we don't have that. Okay, number 15. It said when we plot points that corresponds to pairs of data on a coordinate system, we call the result a scatter diagram or scatter plot. According to taxifarefinder.com, a cab ride from the airport in Las Vegas will cost you an initial charge of $5.10 plus $2.60 per mile. Use this information to fill in the rest of the table describing the total cost for various distances. Then create a scatter diagram using the distance as x coordinate and the cost as y coordinate. Make sure you label a scale on each axis. Okay, now when we look here, you notice for 0 miles it went to $5.10. 1 mile is $7.70. So that means it went up, what, $2.60. And then mile 2, it went up to $10.30, which is another $2.60 it went up. So we can assume that these will go up $2.60. So it'd be $12.90, $15.50, and then finally $18.10 if we keep adding on $2.60. Now we need to label this graph here. Now as far as this is concerned, this is 0 through 5. So we could do these by ones here. And this would take us to 6 miles, which is pretty good. And then down the side here, we know that this first line here would be 0. But here, we want to go, it's from $5 to $18. It looks as though we could do $2 for each tick mark here. So it'd be 2, 4, 6, 8, 10, 12, 14, 16, 18, and the top will be 20. Okay, so now we have our miles, we have our dollars. Okay, so now we want to plot these points. So for 0 miles, it'll be about 510, which would be a little bit over half between 4 and 6. And then for 1 mile, it'd be 770. It'll be close to 8, but not quite there. 2 miles, it'll be 1030. It'll be a little bit above 10. 3 miles, it would be 1290. So it'll be in between, almost exactly in between 12 and 14. And then 4 miles, it'll be 1550, which would be a little bit in between, a little bit past the middle, in between 14 and 16. And then 5 would be 18. 10 would be a little bit above 18. Now we could connect those points. And there's our graph. It's a little bit off because I didn't have a straight edge, but it's pretty good. Okay, 16. What do you notice about the pattern that the points on your scatter diagram are making? Use that observation about a pattern to connect the points. Drawing a graph that represents the cost of a cab ride based on distance. So it's increasing at a steady rate. So they line up nicely. So the graph lines up nicely because it's increasing at a steady rate. Okay, so now we move on to page 140. Now on page 140, we don't have that many to do on page 140. It says here, we'll return to our cab ride graph in a bit, but first let's talk about drawing graphs in general. 17, what temperature is this thermometer displaying? I have no idea. And the reason why I don't have any idea is because this is not marked with any number, so I don't know what the temperature is. 18, explain why the thermometer is pretty much useless. Marks are not labeled on the thermometer. Okay, 19. What are the coordinates of the point drawn on the graph? Still would be I have no idea. Because if you look here, these are not marked. And then it says, explain why the graph is pretty much useless. There is no scale labeled on the axis. There's no scale labeled. Okay. So now I was debating on whether or not I should go on because 2-3 actually has 3 more pages, but I will save those pages for tomorrow. So thank you and have a wonderful day.